All right, good morning, everybody. I think today's Wednesday. Seems about right. Has anybody, I'm just curious, I'm looking at different things for fall, because theoretically at Lake State, we're going to have face-to-face classes. And usually I do something kind of like we do with the Zoom polling, but it's an in-class poll. But I was just curious if anybody has used Kahoot in a class or if you've heard of that. That is a platform where you can dial in with your cell phones. So I'd just be curious what your feedback was, if you thought it was a good way to measure. All right, so it seems like everybody seems to have, or a couple of you have used it. But if you have any tips or things that you liked about it or didn't like about it, I know it is very interactive and it may be competitive for students, and I guess maybe you can remove some of those things out of there. But I will look into it. So if it's something that students are interested in, I'll look into that for the fall class. So I appreciate any feedback you have on that. Okay, so for tomorrow, we will start and just do chapter 14. It's not a super long chapter. The content of it is similar to chapter 13, but the big things there are ethers and epoxides. The thiols and sulfides we won't spend as much time on. I think that was part B of the video. And one of your labs deals with making epoxides and ethers. I think that's actually next week's lab. So you'll have a chance to look at those in the lab. So your week 1 homework is still sitting there. And then if you've not submitted assignments before on Moodle, that will be a video that you can watch. And then the labs 1 and 2 are available as well. And at this point, we've covered the content for both of those labs. And the quiz will open up tomorrow. The way to submit your quiz will be a little bit different this time around. There will actually be a place for you to submit the quiz on the quiz itself when you open that first link. And there won't be a second link for you to open to submit the quiz. But there will be a different link when you go to get your feedback. So it'll look like the feedback you'd seen before. I'm still trying to figure this out. I'm trying to make it as seamless or less of a pain in the butt for you guys as possible. So there should be only one link for you to upload your quiz when you're done. And try to, again, you're going to be watching the video on submitting your assignments. And I think for the people that are coming from 225 last week, none of you were notebook submitters, but don't submit your answers on just a plain piece of notebook paper. That makes it very difficult to grade. All right, so for those of you that are in class right now, how many of you are print out the quiz and do it before submitting it? If most people are printing out the quiz, then I can have a PDF available, because that makes it a little bit easier. Right, so it seems like most of you are printing things out. If you submit with the Word because you're answering questions in there, that's perfectly fine as well. Or if you're doing a hybrid of both, that's perfectly okay. All right. So we're going to jump into this synthesis problem. This was a leftover from the CPA part C. And so we're just going to kind of, I'm going to go with the majority on these. So we'll start our synthesis. And for each step, these are the most of the steps here for the synthesis. And then we'll go through it and see what is going to work and what doesn't work. So if you're looking at this molecule, what should we do in the first step of this molecule? What do you think we should do first? Okay, so we have a tie on adding carbons or eliminating bromine. So let's go with, if you are going to add carbons, for those of you that wanted to add carbons, how would we add the carbons? So what ways would you want to add the carbons? Are we going to go through an alkyne? Are we going to do some sort of SN2 reaction? Or are we going to do a Grignard? So if you didn't vote for carbons, but at this point, if you wanted to add carbons, how would we do that? So go ahead and enter that in the chat when you come up with that. All right, so what ways would we add carbons here? We can go through a Grignard or an alkyne. Those are their two big reactions for adding carbons. So let's say A for Grignard, B for alkyne. Okay, so the majority of you look like you want to do Grignards. So if we go the Grignard route, I'm going to use magnesium to make this compound into a Grignard because the Br is already there. All right, and right away, this step is actually going to be problematic. An alcohol cannot exist in the same molecule as a Grignard. Likewise, we can't have a Grignard in the presence of an alcohol. So what could happen is this H, or yeah, the C minus that's on that carbon with this plus magnesium here, that can deprotonate another alcohol. Make the alkoxide, and then that becomes O minus. And then we lose that whole Grignard, and there's an H that got picked up here. So this step is not going to work. We don't want to make the Grignard first. So because we know that a Grignard is a really good way to make our carbon additions, and so we want to use the Grignard down the line. But in order to make that Grignard, we need to do something with the alcohol. So we actually want to protect that alcohol first. So again, we can't make the Grignard first because the negative charge will deprotonate the alcohol instead of being able to add it to something else. So to protect our alcohol, we're going to use TMS chloride. That'll put an OTMS here. And then if you notice in the second molecule, we don't have a double bond. You can reduce the double bond at this point using H2 platinum. And for these two steps, you could actually switch them around and that would not have an effect on the molecule. So if you wanted to reduce your alkene first, that would be fine. And previously, I know we said that adding carbons is good to do first, and that usually is true. But if you have a functional group on there that is going to react negatively in a way that we don't want it to, then you have to take care of that one first. So we've protected our alcohol, and our bromine is there. So now we can convert that into a Grignard. And what do we need to add to it to add our carbons? What reagent is going to get added? How many carbons are we adding? So we're adding 3 carbons at that position there. So what we can do is take our carbonyl and add the 3 carbons. And if you recall, our Grignard, once it attacks the carbonyl, is going to form an alcohol. So now I need to oxidize that alcohol to the carbonyl. And there are several reagents that you can use. Since it's a secondary alcohol, you can use the harsher oxidizing reagents if you want, or the milder ones. So on this one, we can just use PCC. So that will take the alcohol down to the carbonyl. And then the last step to get to our target molecule is to deprotect the TMS group. And to do that, we use tetrabutyl ammonium fluoride, or TBAF. All right, any questions there? So that is a longer synthesis. There will not be one that long on the quiz. It'll probably be a 2 to 3 step question if there is a synthesis one on the quiz. I have not written it yet, so I don't know what's going to be on it. All right, does anybody have questions on any of those steps? All right, no questions. We'll look on to the next problem. Okay, so this is just a little bit of a couple of problems from yesterday's stuff, just to jog our memories here on how to transform our OHs into something else. So what reagent could we use to do an alcohol to a bromine where we switch the stereochemistry? Good, we're going to use PBr3. And that will invert the stereochemistry. Usually what happens is the OH attacks the P because OH or oxygen really likes P, and one of those BRs will get kicked off. So one of these gets kicked off. So this huge thing now is a really great leaving group. And that Br minus that was kicked off can act as a nucleophile and kick that off. So that'll do an SN2 attack, which is how we get the inverted stereochemistry there. All right, questions on that one? All right, how about converting the OH to a Cl? Good, SOCl2. You can also use zinc chloride to do that reaction as well. And the mechanisms for these are all similar. The oxygen's going to attack that S, or it's going to attack the zinc, kicking off a chlorine, making a good leaving group, and then the chlorine will come in and kick there. So for E and B, even though stereochemistry is not indicated, the reactions are the same. For the OH to Cl, we use SOCl2 again, or zinc chloride. And then for the Br, you can still use PBr3. So these reactions work with primary alcohols, secondary alcohols, or tertiary. All right, very good. Okay, so these are our products of Grignards. So do these two Grignard reactions and then just jot down what you think is the product that is formed. And then I'll throw up a multiple choice answer in a minute here. All right, so what did we get for that first one, letter A there? All right, so those of you that voted selected B, which is the correct answer here. So you want to recognize that when you have that MgBr, whatever is next to it, which is this carbon, is negatively charged. So that's going to act as the nucleophile to attack right there. Those electrons will come up. So you have an O minus plus this new CH3 that you added. And then in the water workup, that gets protonated to form the alcohol. All right, what about B? What does that look like? All right, good. So most of you that voted here said C, and that is the correct answer here as well. So we're just going to add one CH2CH3 group, and then we get the tertiary alcohol there. All right, what about C and D here? What is our product going to be for C and D? All right, very good. So you all chose B. That is the correct answer here. So we're just going to add that magnesium phenyl bromide, and that will add a bond from here to that carbonyl. So that's what we get there. What about D? What is D going to look like? All right, the consensus seems to be C. Some of you are unsure. So the Grignard is the one acting as our nucleophile. This is our electrophile. So this carbon that's next to the Grignard is the negative charge. That's going to attack here, which brings those electrons up to there. So I've added the ethyl group. This is O minus. And at this point, if oxygen has an opportunity to bond to double bond to carbon by kicking off a leaving group, it will. And oxygen or an ether OR group is a great leaving group. So this is going to come back down and kick off this leaving group. So I reform the carbonyl. And then Grignards can still react with carbonyls, esters, or the ketones or aldehydes. So this one is going to now attack here. And then we'll get protonation or a proton transfer to get to the alcohol. So C is going to be our answer on that one. Questions there? All right, major products here. We have an alcohol secondary that gets added to tosyl chloride. Tosyl chloride is different than TMS. TMS is the protecting group. Tosyl chloride is the one that makes an alcohol a good leaving group. So that would be the first reagent. PY is pyridine, which is a mild base. And that just helps to push the reaction along. And sodium ethoxide here is a base or nucleophile. And if I remember correctly, this one reacts as both. So you could get an elimination product, or you could get the substitution product. All right, what happens with excess chromium acid? This is the equivalent of NaCr2O7. So what product are we going to get here? All right, so a lot of you chose B because you recognize that this is an oxidizing reagent. So it will oxidize a primary alcohol to the carboxylic acid. We have excess of this reagent around. So if you look at your reaction tables, we also have an entry where an aldehyde can get treated with the same reagent and also produce a carboxylic acid. So we're going to get 2 carboxylic acids when we have excess chromium H3O+. So as long as there are hydrogens on that carbon to the oxygen, then there will be an oxidation there. If we had this alcohol, the only one that can get oxidized is the primary alcohol. So we would see this as a product here. So the tertiary alcohol gets left alone. But the primary will get oxidized all the way to the carboxylic acid. So as long as you have a hydrogen, here we have 2. As long as there's a hydrogen present on that carbon to the oxygen, that's going to go to the carboxylic acid. But on this particular tertiary alcohol, there's no hydrogens there, so that one does not get oxidized. All right, questions on the last one? This one is an alcohol and an aldehyde with DMP, which is the Des-Martin pyridinane. That one acts like PCC. So what is our product going to be there? What functional group will we get? So this one is a milder reagent. It's going to do nothing to the aldehyde. And we're just going to oxidize this alcohol to the aldehyde. So that will be our product right there. Questions on that one? All right, here we're looking at a synthesis problem. We're adding carbons. Adding 7 carbons. Our alkyne is gone. Now we have a ketone. So there's a couple of different ways probably that you could approach this. In this case, I don't have to worry about multiple functional groups to try to protect things. I'm just going to go ahead and add my carbons. So if I label these 2, I can think about this and this being those 2 carbons, or you could do it from the other side as well. So there's going to be multiple answers here. If I start with those 2 as being my AB, I'd need to add this 1 carbon to the left or the right side. And that will be with NaNH2. Followed by water. So I'm adding that 1 carbon. On the other end, I need to add 4 carbons. That should be CH3Br, sorry. Here I'm adding 4 carbons. So I've added my 4 carbons, and then I can make that into the ketone using water, acid, and HgSO4. So places where order doesn't necessarily matter is the 2 additions of the carbon steps. So you could have added the 4 carbons first or the 3 carbons first. So if I was numbering these steps. So what you could have done the synthesis in 2, 1, and then 3. What you would not want to do is make 3 first, just because then you'd have the ketone and you would have a harder time adding carbons that way. If you wanted to go through the alcohol and then make a ketone and then do a Grignard, I suppose you could do that as well. But those would probably take more steps. So this is probably the more efficient way to do this synthesis. Any questions there? All right, how about this one? Does anybody have any ideas for this one? All right, so the only thing that's changing here is that we're adding a methyl group. So we can add carbons through an alkyne or a Grignard. The alkyne doesn't seem very feasible here because that would be quite a bit of extra work. And also we're not adding carbons to the end, so that would be a reason to not use the alkyne. We're adding it to the other carbon, so you might want to think about using a Grignard with a carbonyl. And a carbonyl won't take too much to get to because we already have an alcohol there. So to get to the carbonyl, you can use any of the reagents we have for oxidizing. So PCC is always a popular one. There's the DMP. You can use the Jones reagent. You can use KMNO4. All of those will get you the ketone because it's a secondary alcohol. And then to get to the alcohol here, we add our CH3 Grignard, followed by water. Any questions on that one? All right, here we're looking at mechanisms, and we're looking to make this cyclic structure here using sodium hydride, and we have an alcohol in place. Our first step is going to be a proton transfer. So this H is negatively charged. It's going to grab the most acidic proton, which is the alcohol proton that has a pKa of around 16. So it'll take that proton. The electrons from the oxygen to hydrogen will go on to the oxygen. So that will be negatively charged. Now the oxygen is going to be acting as our nucleophile, and that C to Br is the electrophile. So the nucleophile is going to do a nucleophilic attack or hug on the electrophile and kick off our leaving group. And if I count the number of things in the ring, I have 1, 2, 3. It's going to be a 6-membered ring, oxygen. That's carbon for the number 2, 3, 4, 5, and then 6. And then my new bond was created right there. So that's how we would do the mechanism for that particular problem. And this functional group is an ether that's used, made using an alcohol. So we'll see more of that tomorrow. Okay, so here we're looking at different reactions. We have the end product. Compound A we know has 6 carbons, 11 hydrogens, and a bromine. It reacts with magnesium to make compound B. So we're probably forming a Grignard here. And then we're going to add acetone to that to get compound C. If there's a Grignard reacting with a carbonyl, we're going to get some sort of alcohol here. And concentrated acid or sulfuric acid plus heat is going to eliminate that alcohol. So you can kind of pick things apart. Compound C, we're looking at an alcohol. If I think about what alcohols could come from this alkene here, the cyclohexane alkene, and I look backwards, there's 2 different alcohols that I could come up with. So those are 2 possibilities for structure C. So looking at what we're adding from B to C, which do you think is more likely to be compound C? All right, so it looks like a lot of you are opting for B. And we'll take a look at this a little bit more closely here. So if this Grignard structure compound B is whatever it is, it's going to attack this carbon right here. And when it does that, the electrons are going to go onto the oxygen. So the oxygen, or the alcohol, is on the same carbon as where those 2 methyl groups are. If I look here, the methyl groups are on this carbon. The alcohol should be on the same group as the methyl groups, which is going to be A. So if you chose A, that is the correct structure for C. So that one is compound C. So again, the alcohol forms on the same carbon where those methyls are that were added, which is how we got to structure being A. All right, and for B, we're looking at a Grignard reagent. If we know now that this part of the structure came from the acetone in B, our Grignard reagent should be that one right there, magnesium bromide. And then from A, we're just inserting a magnesium there, so this should be bromocyclohexane. All right, any questions on how to get those ones? All right, here's another synthesis question. Using 2-propanol as your only source of carbon, how would you make 2-methyl-2-pentanol? So 2-propanol looks like that. That's the same as isopropanol, which is rubbing alcohol. And we need to make 2-methyl-2-pentanol. Okay, so we have to make all of our reagents here. Anybody have ideas on how to start with this one? If I'm looking at this molecule, the 2 methyl groups here with the OH look like this. So I think that something is attacking that initial one as a Grignard, where this other part here is my Grignard. And what I mean is that I have acetone or 2-propanone plus that reagent there. So how would I make acetone and that Grignard? Okay, so if I was going to start with the 2-propanol, I need to get to the acetone. This is an oxidation because we're losing hydrogens here, so you can use your favorite oxidizing reagent. So let's say you wanted to use DMP here, the Dess-Martin pyridinane, you could do that. So that would be part A. So you have your first intermediate. Now I need to make this Grignard, the propyl magnesium bromide from the alcohol. This one's going to take a couple more steps. So I need to move that alcohol to the end and then put a bromine there. And right now our alcohol is a bad leaving group. So I'm going to make it a better leaving group. Let's see, I use SOCl2. That will make it the chlorine. You do an elimination. You can use T-butoxide or DBU-DBN. Any of those will work to get the alkene. Then I need to make my bromine on the end. So you can use HBr with peroxide. That will give me the anti-Markovnikov bromine. And then I can just add magnesium to make the Grignard. And then when I add A together with B, I should get the target molecule. Does anybody have questions there? All right, here we're looking at different products. So why don't you guys attempt this one? I'll give you a couple of potential answers, but this is a 3-step reaction. So there's going to be 3 different things that happen here. All right, let's take a look at this one. So in the first step, we have acid, which can also be H plus and water if you separate those out. So what that is going to do is add an alcohol. So for step 1, we get an alcohol. Step 2 is the Jones reagent, which will oxidize the alcohol. Since we only have one hydrogen there, this is going to oxidize to the ketone. So that's after step 2. We're not going to get any alkene cleavage with ozonolysis here or anything like that. So C won't be our answer. And A is our intermediate. We still have one other thing to do there. So A is not correct. And then in the third step, we're adding phenyl magnesium bromide. So that pH here, that phenyl group is going to attack there. We're going to form an alcohol. So we'll get pH and OH there. So our answer is going to be B. If you wanted to make D, what you would need to do is make the diol. So you could do that with osmium tetroxide or potassium permanganate. And then for the first step, and then follow the rest of the synthesis there. So that's how you could get to D. But our answer for this one is B. All right, does anybody have questions there? All right, we have a mechanism question next. So this is a mechanism for the Grignard reagent that's reacting with an ester. So we kind of saw one of these mechanisms a little bit earlier today. This one has excess methyl magnesium bromide. This is our nucleophile. Here's our electrophile. The nucleophile, the methyl part, is going to react with this and bring those electrons up. So we'll have a negative charge, and I've added my CH3, or that methyl group. And then I mentioned earlier that if carbon has an opportunity to form a double bond again to carbon while kicking off a leaving group, it will do that. So this OR here is my leaving group. These electrons will come down to form that double bond, and it breaks this bond here, so that becomes O negative. And there's a new double bond formed there. If you want to keep tabs of your carbons, you can just number those. So we still have more Grignard reagent floating around. So there's a question says we don't add 2 methyl groups because of excess. We are going to add 2 methyl groups. So the first one already got added, and then we're about to add the second one right now. So the first one gets added first, and then we get this intermediate here with the ketone that reforms. And then that second methyl group can now add to the ketone, because Grignards can still react with ketones. So I have the second methyl group here. Then there's an O minus. I get a proton transfer with the water that's present. So both of those negative charges can pick up that water. So that is our product. So you can see those 2 methyl groups right there in the original product. There's 5 carbons in between there. So there is our product. All right, any questions there? So excess methyl magnesium bromide is going to add 2 of the Grignard reagents and create a tertiary alcohol in the process. So if there is excess, then the 2 will get added there. All right. Here is another synthesis problem. We're looking at a carbonyl. And we also have added 1 carbon. All right, so things that we could do here, if we're adding carbons, you could go through the alkyne. That might take a lot more steps, but we want to, since this is chapter 13, get on our Grignard track here. So I can add, make this into a Grignard. So Grignards don't have to be bromines, they can be chlorine. So I can add magnesium here. So that will be magnesium chloride. And to this, I am going to add, let's see, 1 carbon. Actually, this might not work the way that I'm doing this. So and I'll tell you why. If I add this right here, this is 2 carbons. If I add 1 carbon, formaldehyde, all right, there's my original 4 carbons. This is the second one, and I would get an OH here. So that would put my carbon in the wrong position. So what I need to do instead is make this original 4 carbon chain what is getting attacked. So I need to convert this to an alcohol. I'm going to oxidize this only to the aldehyde, so I can use DMP. So I have the aldehyde, and then I want to add methyl magnesium bromide and water. So that will add that second group carbon there, and then I can continue on with the oxidation, and I can use any oxidizing agent here. I can use the Jones. So I can use that acid. So that first thing that I started to do, I thought would work, but after I looked at where the carbon was adding, that was in the wrong position. So this one is not going to work. So that magnesium first isn't going to work, followed by the second step because of the location of the alcohol. All right, I think we got a couple more problems. I'm gonna fire this back up here. All right, so did anybody have questions on that last problem that just went away? This one here. So you want to make sure the alcohols and your carbons are adding in the right position. If it added to the wrong spot, you could go through and put it in the right spot. It just takes some more steps. So sometimes you can have longer syntheses that work, but sometimes a few steps will do and you don't need to do it long. All right, how about this one? This one could be a one-step synthesis. So this one could happen in one step. What one reagent could you use? Ideas for reagents here. So we're just adding these 2 carbons. So we just need those 2 carbons, magnesium bromide, and water. That one maybe looks worse than it actually is. All right, questions there? All right, last one. Here we are adding carbons as well. Adding 1 carbon. We're going from alkene to alcohol. And this is going to be a similar situation. This is the Grignard that is getting added right there. So I need that to attack, and maybe I should have done a retrosynthesis on the last one. I need to attack that carbonyl with the CH3MGBr to get the correct product. So I need to shoot to make that carbonyl. And to do that in the forward direction, I need to have an alcohol in place at the end. The reactions that I know how to do that are BH3 and then peroxide. And then to get to the aldehyde, I can use the Swern oxidation. Or you could use PCC or DMP. You don't want to use the Jones oxidation because that will go to the carboxylic acid. So that gets you that aldehyde. Then we add methyl magnesium bromide and water. Okay, any questions there? All right, that was the last problem that I had for today. If you have questions on this or any other things, you can hang around after class and ask at that time. Otherwise, have a good rest of the day. All right, both of you may have questions. Who's first?
Doesn't matter to me. I can shoot.
Go ahead.
I did a question like almost at the start. It was like with a ring and an MGBR on the ring. I don't know if you can find that question. There was no like number on the top of the slide.
Oh, those were, was it the first one?
It was like at the start. I don't know if it was the first, but
This one?
no.
One of these?
Close. That one.
This
Back
one?
That one. I don't understand how you got the ethyl group coming off of it.
I may have moved it. So it may have been on a different side, maybe than what you're used to seeing.
Right.
So if you, this is going to attack here. So if you drew it this way or this way, either of those answers are the same thing.
Okay.
Was it, I think maybe I drew it the second way.
Yeah, exactly.
Yep.
Okay.
So it's the same thing. It's just they're just rotated around.
Okay. Awesome. Thank you.
Yep.
I just had some questions with the lab.
Sure.
So at my old school, or like where I attend normally, we didn't touch a whole lot on reading like the NMR and stuff like that.
Okay.
And that's a lot what this lab is about. So do you have any like recommendations on how to like resources or something? Because I started the lab and then I got stuck on some of the questions because I couldn't read that.
Okay. There is, let me try to think. Did you try the refresher video on a spectroscopy? There's one on Moodle in the lab section.
Okay. I'll try to find that then.
That one, otherwise I'll send you 2 links on, trying to think. You didn't do spectroscopy at all, huh?
We did it like a little bit, but not much.
Okay.
And so originally, so I actually have taken Orgo 2 before. I just ended up having to take a W. I had a lot of health issues, so my grade
Okay.
was dropping super
Mhm.
low. And they started to cover that like at the end after I had taken that W.
Of
and
Orgo
went
2?
through. Yeah.
Okay. So what then I would recommend for you is I'll send you links to them, but we did chapter 15 and 16. Those are our IR and NMR spectroscopy chapters, because I cover that in the first semester so that we could integrate that into lab. So just so you have that information, and just do your best with what you can. If you have questions, I can help you, figure out where protons and stuff are. But you won't have to, I won't on an exam blanket give you spectra and expect you to solve the structure, because we did that last semester
Okay.
already. So
Yeah.
in the
I
lab,
use
just do the best that you can, and I'll just remember to be more lenient with your grading on
Okay,
those
thank you. I've
things.
answered most of the questions in the lab,
Hmm.
just like the best I could so far. The problems I was like, the question I was really stuck on was trying to figure out like it was like the actual yield and percent yield with what I was given. Because normally like I'm in the lab and I'll just like like weigh it or get the
Oh yeah. So
because I've also never used that lab before. I did watch the video though
yeah.
before I tried it yesterday.
So the masses and stuff that I gave in the tables, those are like made up things, because you would in the lab weigh stuff out and then figure out your percent yields.
Okay, so I just have to use that stuff in the table from the lab.
Yeah, so that one you should incorporate
Okay.
into your lab notebook. If you don't remember how to calculate that, there is in the example lab on the lab tab. Let me see
Yeah.
how to figure that out. So, but most of the thing, yeah, there's an lab report example, a notebook example.
For
For
everything else, I was just trying to like look things up on Google and try to like, okay, I think this sounds right and things like that because I was
yeah,
not
so
sure.
check out the lab report notebook example, and then it will tell you how to calculate the yields. Basically, if
Okay.
I gave you the mass, you just have to convert it to moles. To figure out and then you got to figure out from your starting materials, which is the limiting reagent. So let's say I use 5 millimoles of starting reagent and then like 6.5 of the osmium tetroxide or something. The 5 millimoles, because it's less, is the limiting reagent. So at most, you can make 5 millimoles of product. So that's how you would get to the theoretical yield.
Okay. Yeah, and then like for reading like the NMR and stuff like that, I was looking it up, but I was like not sure like how reliable, like how right some of these websites I was finding would be. That's why I was a little like lenient about using them, but
Okay. So the spectra that's in the virtual lab is from Sigma Aldrich. So they take spectra of their compounds. So if you came up with it in your lab, and usually the peaks are numbered, if in the proton, they're numbered with different numbers. And if there's extra stuff in there, usually you have a mixture of compounds. The ones that are pertinent to your data are the ones that are numbered for proton. But
okay.
those should be reliable if you made the correct product, if that makes any sense.
Yeah.
And then, yeah, anytime if you want to ask questions, just drop me a line and we can just pop on to Zoom and I can try to answer them for you.
Okay, thank you.
Yeah, but I'll try to help you as much as I can. But I'll refer you to the chapter 15 and 16 lecture videos. At least that will give you kind of an overview of what IR is going to tell you about functional groups, and then what you'll find with NMR as well. But you won't have to go that in depth with the solving of the structures, because in this course, I'm just having people assign structures or protons to structures. So if you look at where a chemical shift is, things that have higher numbers are closer to things that have more electron density. And so if it's next to a carbon or a hydrogen next to an OH, that one's going to have a higher number. So it's kind of those kinds of things. You won't have to just solve the entire thing. So
Okay, sounds good. Thank
yep,
you.
I'll send you links to those videos.
Is it the same like so it matches up with the chapter 15 and 16 in the textbook?
In what version of the book do you have?
Let me
This is
check.
the second edition.
Yeah.
Yeah, if it's second edition, yeah, it'll be chapters 15 and 16.
Okay.
Yep, and then I'll just send you those videos over. I'll send you the links to those so you can check those out.
Okay, thank you.
Yep. Yeah.